A very good morning to everyone. Uh, I, Rinku Bhatia, welcome you to yet another day of 1 week national workshop on advanced synthesis and characterization techniques, organized by Department of Applied Physics, Amity School of Engineering and Technology, Amity University, Madhya Pradesh. The speaker for today's session is Dr. M.P. Sharma. Let me first introduce you to our honored guest. Dr. M.P. Sharma is Assistant Professor at Department of Pure and Applied Physics, Guru Ghasidas Vishwavidyalaya, Bilaspur. Dr. Sharma did his BSc from MDS University, Ajmer in 2000, then MSc from IIT Mumbai in 2002, and PhD from University of Rajasthan in 2009. He has joined Guru Ghasidas University from July 2010. He has to his credit awards and scholastic achievements such as CSIR SRF extended from 2009, May 2009 to May 2010. Then he has JRF SRF from CSIR Net 2004 to 2009, and he has also qualified GATE in 2002 and 2004. He is a member of technical societies such as Life Member of Nuclear Track Society of India, Life Member of Indian Physics Association, Life Member of Indian Society for Particle Accelerators. He has more than 33 papers published in international and national journals, and he has attended more than 30 conferences, seminars, and workshops. He has delivered number of talks in symposiums and seminars. His area of research includes material science, material preparation characterization, oxide-based ceramics, multiferroids, magnetic materials. May I now request Dr. M.P. Sharma to kindly deliver his talks.
Thank you, Madam Rinku Bhatia, Madam. And also thank to Amity University to organize such kind of the workshop. So today, I'm also thankful to the Dr. Pankaj Mishra and Dr. Manisha Singh to invite me for this kind of session. So in this session, first I am share my screen, so you can. So it is visible, Madam?
Yes, sir, visible now.
Yeah, it's okay. So today I will cover on this topic. The topic is a vibrating sample magnetometer VSM techniques. So in this technique, first we have to discuss about the basic physics of magnetism and type of the magnetism and its properties and number of method to measure the magnetizations and how to analyze the VSM result, or you can say the magnetization result from your experimental point of view. So this time. Okay. So well known, the magnetic materials is very common for all of us. Okay. So magnet are well known as a common items in our workplaces and household. So we are using a magnet as a holding some of features and some of the switches, and there are a lot of application as a electronic switch and remote, and everywhere we are using the magnets or magnetic properties. So generally the most of peoples are familiar this general property, and the traditional concept of magnetism is around the magnetic field, and basically it is known as a dipoles. So term is magnetic field is a simply it describes the volume of the space where is a you can say is a dipoles is a change. Okay, so this change in energy can be detected and measures using there is different kind of instruments are there. So location where is a magnetic field can be detected and excited entry in the material is called the magnetic poles. So generally we have to be known as a magnetic pole. So we are also is saying the earth having a north pole, the south poles and so on. So magnetic pole have never been detected in the isolation, means is monopole cannot be exist in a nature due to the uh, dipole natures. So what is a dipole? Dipole is an object that has a magnetic poles on one end and second end, but having the opposite in a magnetics. So it is a can be. So now what is the source of so source of magnetism? So in a material, if you are talking about the material, so material is a composed of the atoms, and atoms are having a lot of protons, neutrons, and electrons. So generally, is a proton and neutrons having in a nucleus, and electron is a uh, rounding and surrounding of this nucleus. So this rotation of the electron and the spin of the electron, it is give the magnetization. So electrons carry a negative electric charge and produce a magnetic field as they move through the space. Means we are saying that if the electron is moved, the current is flow, and there is a current is there, then you can say is a magnetic field is there. And if the magnetic field is there, so you can say is a current is there. Okay, so current and the magnetic field is interconnected. So magnetic field is produced when there is a electric charge is motion. So the strength of this field is called the magnetic moment. And when is a material is placed within a magnetic field, the magnetic force of the material's electron will be affected. And this law is known as a Faraday law, means that the change in the field with the time, and it's developed the EMF. This is called the Faraday law of the magnetic inductions. So on the this property, you can say the magnetic moment associated with the atoms have three origins. One is a electron orbit motion, another one is a spin of the electrons, and the next one is a change in the orbital motion caused by the external magnetic field. So these are the main factor which introduce the magnetic field in the materials. So now the most of the atoms electrons occur in a pair. So electron in a pair spin in opposite direction. So we can say is the electrons are paired together, their opposite spins cause their magnetic field to the cancel out each other. So you can say is there is a no magnetic moment or you can say is a magnetic field is exists. And materials with the some unpaired electrons, means if you are the electron is a pairing, then we can say in the same direction and opposite direction. So if your electron is unpaired electron, so we'll have some magnetic field and will react as a external magnetic field. So most of the material can be classified as a three types of the materials as a diamagnetic, paramagnetic, and ferromagnetics. So these are the ferromagnetic, antiferromagnetic also is a one of the class, but in this class we have again is a subclassified as a ferrimagnet and super paramagnetic. And diamagnetic also is classified as a weakly diamagnetic and strongly diamagnetic, which is are the superconductor. So these are the some arrangement of the spins, or you can say is a moment. So in this figure, there is a spins are aligned in the same direction. So we can say is a ferromagnetic, and there is a antiferromagnetic beam, and C1 is a ferrimagnet. Means we can say is the magnitude of the spins are different in the direction. One is having a larger one and the second one is a small one. So need magnetization can be in one direction. So we can classify it as a ferrimagnet. It is is a type of the ferromagnetic. So now is what is the diamagnetic? We are explaining in details. So magnetic diamagnetics having very weak and negative susceptibility, and susceptibility is defined as a magnetization per field. So these materials are slightly repelled by the magnetic field, and the material does not retain the magnetic property when the external field is removed. Means when you are applying the external field, there is no magnetic property when we are removed. So dynamic materials are solid with the all pair electrons, resulting there is no permanent net magnetic mode per atoms. So in the diamagnetic materials, there is all the electrons are in a pair condition. But when you are applying the field, then it is a the pairing is directional, so we can choose the magnetic in opposite of the applied fields. So diamagnetic property arise from the alignment of the electron orbit under the influence of the external magnetic field. The most of the element in the periodic tables are is considering as a copper, silver, gold. And what is the paramagnetic? Paramagnetic means there is a having a some permanent dipoles. So having as a small and positive susceptibility to the magnetic field. So these materials are slightly attracted by the magnetic field and does not retain the magnetic property again when you are applying the external field. So paramagnetic property are due to the presence of some unpaired electrons. You can say that there is a some permanent dipoles are there. So from the alignment of the electrons, it is orbit is caused by the external and shows the some magnetic. So paramagnetic material are the examples as a magnesium, molybdenum, lithium, and titaniums are there. And now is the next one is a ferromagnetic materials. So ferromagnetic materials having a large and positive susceptibility in case of the external field. So they exhibit a strong attraction to the magnetic field and are able to retain their magnetic property after removing the external field. So ferromagnetic material have some unpaired electrons, so they have some net magnetic moments and they get their strong magnetic property due to the presence of the magnetic domains. So in these domains, there is a large number of atoms, moments, magnetic moments you are saying. So it is a range of 10 to 12 to 10 to power 15 are aligned in parallel to, so that the net magnetization is very large, or you can say is strong. So when your magnetic material in the unmagnetized state means like this one, this is the condition. When your material in unmagnetized, then the domains are randomly orientated. But when you are applying the external magnetic field, it is aligned to the direction of magnetic field. So when a magnetization force is applied, so domain becomes aligned to the produce a strong magnetic field within the part of this one. So the example of this one is iron, nickel, and cobalt are the best example of ferromagnetic materials. So there is a some measurement, or it is a uh, loop. It is saying the hysteresis loop. Hysteresis loop means the physical property lags behind some change in the effect. Means hysteresis is information it is give to type of the magnetization, maybe is a ferro, para, or dia, or super paramagnetism, whatever you can classify it using this BH curve. This also is called the BH curve. And this curve there is a line is green line, it is shows a paramagnetism. When you are applying the field, the magnetization is increasing. In case of diamagnetism, when you are applied the field, the magnetic field is produced in opposite of the applied field. So that is in a negative direction. And then the ferro one, when you are increase the field, the magnetization increase and goes to saturation and then come back to the. So when you are applying the field is 0 again from higher to 0 1, it is not come to 0. And this case, this is called the hysteresis, means it is a the property is behind to the magnetic field, means the magnetization is not become to 0. So this is the case of the ferromagnetic. And this one, it is a super paramagnetic. Nothing is a super paramagnetic, is a the special kind of the paramagnetism. When you are talk about the bulk to nano, then it is behave as a super paramagnetic. So now what's the electron spin? Generally electron spin the surrounding the in a circle, then the moment is given by is called the Bohr magneton, and mu b is defined as a EH upon 4 pi m, that the value is 0.93 into 10 to the power minus 20 EMU. So when we are talking about the iron, so iron is looks like the electron cell configuration. It's given by this one. The atomic number of the iron is 26, and 1s is again is opposite, and 2s opposite, 2p, and last one is 4s is also is opposite. But in 3D there is some different configurations, and on the behalf of this configuration you can classify it as a different kind of the ferromagnetic. So what is the region of the ferromagnetic in the materials? So ferromagnetic materials get their magnetic property only because of their atoms carry the magnetic moment, but also because the material is made of the small region known as a magnetic domains. So this is the picture. It is taken by the magnetic force microscope image. In this one, it is shows some magnetic domains, and there is a domain walls also is seeing this one. So in each domain, all the atomic dipoles are coupled together in a peripheral directions. So this alignment is developed the external as a material develop as a crystalline structure during the solidification from the molten stage. So magnetic domain can be detected using this MF image technique. And why the magnetic materials are subdivided into domains? So the reason is saying that any system can be exist in only minimum energy states. So we know that the system will always be in a state which is the energy is minimized. So due to this one, the domains are divided into some regions, or you can say the domain balls. So we have to explain that why the subdivided state has a small energy than the uniformly magnetized state. So generally, domains can be explained in four type of energy. One is called the exchange energy. So exchange energy is nothing is the exchange energy nothing is the nearest neighboring is significant and result in parallel alignment of the magnetization. So ferromagnetic materials is due to the exchange energy, and it is given by minus 2 J SI SJ. Where is J is a Heisenberg exchange coefficient, and this is a spin due to near one. And next energy is called the magnetostatics energy, and this one is due to the uh, magnetostatics means the why is a magnetic materials is not always be uniform magnets like this so one. So this is shows the spin of the or you can say is the domain of the system is aligned in one direction, and this is goes to in two. So energy is releasing and minimum state and again. So we can say is a ferromagnet is divided in two and then is 4 and finally it is given in E1. Figure is a small SG domains due to the magnetic energy. So there is a structure energy, or we can say the another is an anisotropy energy. We can explain as a magnetic anisotropy. It is due to the crystal nature, and this crystal nature can be give the especially in the single crystal. So directional can be explained using the anisotropy energy, and another is a magnetoelastic energy, which is can be explained as a when your magnetic field is applied, the material maybe is a expand or maybe is a contracts. So when you are applying material, the length is a change. The length is very slightly is less, 10 to the power minus 5. But for energy purpose, it is very important. So some of the material can be expanded or some of material can be contract. So this one is called the magnetostrictions. So change in the magnetization of material result in the elastic distortion, and this one is called the magnetostatic energy. So finally, there is a sum of basic definition of the magnetic field. One is a induction, one is a H and M1. So H is a external field and there is a uh, material property, and then magnetization is the average magnetic moment of the magnetic materials can be given by M. So your chi can be defined as a M is equal to chi of H, where is a susceptibility and this is a tension. So this is mu is a permeability of the material. So now these are the some of definition of a magnetic field, where is a H and B or F or M. The unit is a different in the SI unit and CGA unit. Generally, we are using as a SI unit is ampere per meter, Tesla, Weber, or ampere. So now this is the draft of BH curve. Okay, so BH curve, or you can say is a history loop, or MH curve also is sometimes called. One is BA or H or M or H. So on the basis of this one, we can classify your material on the behalf of this one. If your material the stereogroup has wider one, means red one, so it is having a low permeability, retentivity, coercivity, reluctant, and residual magnetization. In inner one, there is a the loop is lower one, then you can say higher permeability, retentivity, and coercivity, and reluctance and residual magnetization. So in this case, if you are talk about this one, the initial condition when you are applying field is 0, and your samples also is a demagnetized finally. And when you are increasing, the sample magnetization is increasing and increasing and goes to at a saturation point. Then decrease the magnetic field and follow this path. There is a lot of reason behind of this one, and this one is called this point where is cut this x-axis is called the retentivity, and then come to the when your field is negative and the magnetization is 0, then it is called the coercivity, and then again is a opposition saturation, and then come back to the saturation. So on this behalf of, they can also is classified as a hard magnet and soft magnet. So this is the hard magnet having a very large uh, coercivity and remnants, and in this one it is a soft magnet materials. It is a also using this slope you can also calculate it. Okay, so slope at the higher point you can give the permeability. Okay, so this is the example of some soft and hard materials. So this is the alloys, permalloys 78.5 when you are mixing some iron and some other one, and this is the hard magnetic materials. So now what is the method to measure the magnetization? So there is a lot of method to magnetize measuring the magnetization. So magnetization and magnetic sensibility can be measured directly or indirectly by observing any other physical quantity related to these two one. These two one means one is a magnetization or this one. So first method is called the induction method. Okay. So in this method, the voltage is generated through the electromagnet induction. Okay. So magnetic flux can be changed using the uh, change in the magnetic field, or you can insert your sample and movement of the samples. Okay, so this is done provide the change in the value of magnetic induction, which is can be used to find out the magnetization of different materials. So this is another one is a force method. Also is a looks like the same. This method observe the force on the magnetic dipole or materials to find the magnetic property of that materials. Okay, so magneto-optic methods also is there. Electrical method is also is there, and extraction method. This one is based on the VSM technique. So in this method is based on the flux change. So this is the solenoid. We know that the property of the solenoid is give the magnetic field inside is a constant one. Okay, and there is a search coils, and your samples can be moved or extract from this field, and it is generate the EMF in the search coil. Okay, so flux through the search coil of the cross-sectional area is given by phi 1 is equal to mu 0 h plus a way. Okay, and when you are removing this one, the flux is gain, and this flux difference can be calculated by this EMF V is equal to minus number of turn on a this solenoid coil, or this phi can be calculated from phi 1 and phi 2, and you can integrate it, and we can calculate the magnetization of this one. Another one is a vibrating sample magnetometer. This instrument is created by S. Foner in 1959. Okay, so this is based on the flux change in the coil. So when your magnetized sample is vibrate near it one, so this is the magnetic field, constant magnetic field inside of this gap, and there is a searching coil, and this your sample can be movement in the direction of horizontal and vertical, whatever. So sample commonly is a small disc is attached to the end of the non-magnetic rods. So other end of this is fixed with the next one. So this is the structure of the VSM. Okay, so this is the electromagnet. We can say is a Helmholtz coil is there, And this is the pickup coil. This one is pickup coil, and this is the vibrator. You can vibrate your sample in the direction of this one or this one. So in this gap, there is a magnetic field is constant, and when you are vibrating this one, so there is a induce some EMF, and this EMF can be picked up by this coil. The coil is arrangement is next one, and this is the lock-in amplifier. Then can be the lock-in amplifier must be provide the reference signal at the frequency of this vibration to subtract the signal. Okay. So this is the arrangement of the VSM. These are the pickup coil, and this is the sample load. This sample load should be non-magnetic, otherwise some magnetic contribution can be induced in sample one. Okay, so this is the vibration, or like this one or this one, and in this region the magnetic field is a constant. So this magnetic field is constant, and we have to be introduce the uh, change in the field. Do the motion of this one. There is a actual arrangement of the pickup coils. These are the four pickup coils are there. These are winding is different type depending on their signal. So signal is very small, so we have to be use four pickup coils, and you can design as per your. So this is your actual photograph of the VSM. Okay, that magnetic you can say is a locking amplifier is there one, and this is the vibrator. Okay, so there is a motor, motor is there. So this motor can be vibrate on this one, and this is the magnetic field. Allmers coils are there. Okay, and this is the cryostat. You can create a low temperature or high temperature, whatever you need it. So this is the additional assembly. Otherwise, simply the VSM is nothing, is there is a one rod you have to be move in a constant magnetic field, and this moment can be measured using some search coil. So this is the Park Mech model 155. And now another one is a squid magnetometer, which is give high accurate result compared to the VSM. The accuracy of the VSM is a 10 to the power minus 5 AME per gram, and for a squid is a 10 to the power minus 6 to 7 AME per gram. So squid also is useful for the biomedical application. And so superconducting quantum design interference has been key factor in the development and commercialized utilization of the electric and magnetic measurement. So squid is nothing is to be generate the high field, and the accuracy, or in terms of the Tesla, you can say the 10 to the power minus 17. So it is developed by the British physicist Brian David. Jobson discovered the Jobson effect, or you can say is a junction. Josephson effect junction, where is a superconductor. There is two to superconductor. One is the insulating layer, and the current flow in this direction, in opposite and opposite, and the difference you have to be measure. And this is the based on this phenomena. Okay, so now what is the result of the VSM? So VSM result can be taken as a different type of when temperature versus magnetization versus and the time versus whatever you need it, you can take. So in our cases, we have take the sample as a sodium substituted lanthanum magnetite. It is called the sodium 10, and another is a sodium 20. So these are the magnetic moment we have to be measure at from 20 Kelvin to room temperature. Okay, for a sodium one is measurement is ZFC and another is FC. Okay, so plot of the sodium 10 sample as a function of temperature in a ZFC mode. ZFC means zero field cool, means first you have to be applied the zero field and the cool the system up to 20 Kelvin or 4 Kelvin, whatever you have in your system. So this one first cool in a zero field, and then you have to be applied the field as desired. In our case, there is 20 and 200 and 500. So in 20 arrested when applied, and then measuring the measurement in warming cycle in a constant rate of the warming cycle this one. So these are the magnetic moment we have to be recorded. And this one is a field cooled, means first you have to apply the field at room temperature and then cool the system and then take the measurement in the warming cell and the same field, and the difference is give the ordering or disordering of the behavior of the materials. So same sample we have recorded at a different field 20, 200 and 500. The gap is minimizing. Okay, there is a gap 20 and then it is a okay. And this one is another sample, sodium 20. We have to substitute in LaMNO3. So in this case, there is a system is disordered like, and there is a system is order like, means the system you can say the magnetic property is a source from from 20 Kelvin to room temperature. But in this case, the magnetic moment is low and then temperature increasing and again is getting, and there is a some disordering is there. So you can say the system is disordered. Now we have recorded the BH curve at low temperature for both the samples. So sodium 1, we can say the sodium 1 is a good ferromagnet and sodium 20 is a lower, or you can say the disorder magnetic. So in this case, at low temperature, it is a source ferro. There is a some component of the ferro and para one. Okay, this case also there is a magnetic moment is a different. So another one we have to be also verifying this result using the electro transport property, means resistivity with the temperature and is fitting. So it's the same nature we have to be observed in the resistivity also. So now next one is a cerium substituent. The cerium is nothing is a 3 plus and 4 plus. And the sodium, if you are looking, sodium valence is a plus 1 and cerium also is showing is 3 plus and 4 plus. Okay. So when you are substitute cerium 0.5, 0.1, 0.2 and 0.3, the system is got more ordered from disordering. Means at this one it is a disorder and is converted into ordering one. Okay. So same case, it is a different field and there is a MH curve we have recorded at low temperature and room temperature. So room temperature is shows a totally is a paramagnet and low temperature is shows a ferromagnetic nature. We also is observed in this one there is a some ferromagnetic nature at low temperature. So in this case, but the coercivity and eminence is very low. Okay, and these are the MR. So another case we have considered as a cerium calcium substitute. Okay, so in this case we disturb the system as a cerium with the calcium. Cerium maybe is a 3 plus or 4 plus and calcium is 2 plus. So the nature is totally is different type. One is a when your substitute is very low, then you can say the sample is a ordered. Ordered means is a from ferro to para transition, but there is a another observation is there, some peak is there, so maybe is another transition is there, and this one is the system is totally is a disorder. Disorder means there is a some cluster type you can say, and this is the MH curve of a same system La1 2 minus C2x and calcium this one. So this one is a room temperature and this one is 20 low temperature. So it is a when you are substitute 0.5 it is a totally is a ferro sorry is a para, but there is some contribution of the ferro and para. So you can say this system is disorder at room temperature, and low temperature all the samples are shows the ferromagnetic nature. These are the electrical measurement of the systems. So now another system we have taken as a LA 1.5, CA 1.5, Mn2, Fe XO7 means double perovskites or layer perovskite you can see. So in this case, when your system is undoped means LaCaMnO7. So this is the system is a ferromagnetic. When you are substituting the iron, the ferromagnetic is converted into anti-ferromagnetic. There is a peak is decreasing at low temperature. Okay, so this is the nature is shows the anti-ferromagnetic. This one also 0.1, 0.3, 0.5. There is a different field you can see, and this is the BH curve we have measured, or you can say is a MH curve at low temperature and room temperature. Okay, so this is a low temperature. Oh, low temperature, but we have to be prepared different process. One for a solid state one, another is a sol gel one. So solid state and sol gel maybe is due to the some mm nano natures, or you can say is some clustered type is there. So magnetization is different, but the nature is almost is the same. One is a ferro, again is a ferro, this is a ferro, and but there is a some contribution of other components also is there. So you can say the system is a disordered. At room temperature, there is a again is a para one, and this is the resistivity of the system. So we can verify the transition temperature of the uh, system. You can calculate it here. The transition is given here. Okay, from antiferro to para one. It is called the nil temperature. Okay, so this is the MR1 we can measure. We are not started. So now another is a alloy one. Okay, so we have prepared the some nickel copper alloys using the sol gel one, and we have again take the measurement. So this is the sample is shows the from uh, ferro to para transition, and this transition is decreasing when you are increasing the copper. Okay, the parent one, and then copper zero point 0.5, and then copper 1.5. So this is the Curie temperature which is above 1, but this measurement we have take in higher one means using the oven, so room temperature to 900 Kelvin, and these are the measurement at the room temperature and low temperature. Both are the showing the soft ferromagnet. So another one is a reversal of magnetization. So another case we have to be considered as a phase transition and change of the FD exchange interaction, or we can locate as a reorientation of the spin. So negative coupling between the sublattice of the 3D and 4F ions. So this is the measurement of the lanthanum, gadolinium, chromium oxides. One we can taken as a 100 Oersted and 250 Oersted. So at a 100 Oersted, the FC curve is looks like this one, and ZFC is give like this one. So this is the two transition where is the cut the x-axis and the cut the FC and ZFC. So this is the nature of reorientation of the, or we can say is a demagnetization or magnetization, diamagnetic property of this kind of the samples. So this is again there is a 500 and 750. If you are looking this 100 Oersted and 250 Oersted, and the nature is almost same, but the ZFC is move toward. But in the case of the 500 Oersted, when you are applied the higher field, this peak is shifted to the lower one due to the competition with the thermal energy and the domain wall competitions. So this is the decreasing, and finally when you are applied the higher field, it will come like this one. So another curve is 1 hour state is when we are take the higher ones, these are the merged to each other one. So combined effect, if you are looking the total ZFC and total FC 100, 250, 500 and 7 and 1 kilo. So it is transition is shifting towards the lower temperature. So cases what is happening, the T compensate decreasing with the increasing the field and vanishes for the greater than 500 or state. Beyond this, there is no reversal of magnetization. Means the magnetic field energy is higher than the you can say the domain wall energy or whatever magnetic energy you can say. So this is the result is possibly mean the Siemens energy of the high field. Okay, so anomalies is observed that the temperature 2K in the field of the cooling process. Okay, where so another is you can fit the this para curve using the this relation M is equal to M chromium plus C and the internal and applied field and with the Curie temperature and the applied temperatures. Okay, so MRC and these are stand for canted moment of the chromium. Okay, maybe the canted means you can align at the some of angle. Okay, so generally we have talk about the anisotropic energy, which is give the easy direction. So internal field of the chromium can be calculated using this fitting, and the fitting is showing here. And also in this region, there is a region we have plotted as a inverse chi of the temperature. Okay, and this is fitting above the nil temperature, and these are the parameter, nothing else. And the BH curve of the same samples we have to recorded, and this is shows some loops here. So sample has found the spontaneous magnetic moment, but above this one there is a no saturation magnetization there. Only is a paramagnetic nature is shows, but in the lower region is shows as a some ferromagnetic contribution, or you can say is a tinted anti-ferromagnetic ordering. You can say so. Here there is another nature of the BH curve is given here. Okay, when you are applying field and then come back and then it is a decreasing. So this region it is shows as a uh, what? It is diamagnetic to paramagnetic state one. It is a range of the 750 to 1 kilowatt state there in this region. This region it is a behave as a diamagnet. After that one, the field is a higher one. So all the canted spins is lying in the direction of magnetic field, and it shows that the magnetic field is this one. So another one you can say is a super paramagnetic or some contribution of the ferro and pira one. So in this one we have to be discuss about the some nickel nanoparticles is prepared by the borohydride reduction of the nickel Cl2 solution in different concentration. The particle size very low. So in this region you can also is classified as a super paramagnetic. So if you are zoom this one, this is some loop is here, but loop is almost negligible. So we can find out the some contribution of the ferro and pira one, that is the relation. The magnetization is given as a Langevin function and some paramagnetic contributions. Okay, so when you are fitting this curve as a ferro and para one and resulting it is a experimental one. Okay, so this is the ferromagnetic and uh, this one is a para and this one is a ferro, and from this one you can calculate the saturation magnetization MR, MC and chi value also. Okay, so this is the application of your result, different kind of the measurements, and finally we can conclude the nothing is we have to be needs a more sensitive experimental demanding, and uh, the SQUID and VSM. If you are needing more resolution, you go to the SQUID, and today's are there is a micro squid and nano squids are available, but the cost is very high. But VSM it is give only for materials and this one. And finally, it is a think. Okay, if you have any query, you can ask. Hello.
Yes, sir.
Yeah.
I'm just
If
technical.
anybody has any question, can put it on chat box.
If you have any experimental data of a VSM or a skill, you can ask about the result of this one. Otherwise, it's okay.
Participants, any questions?
Participants, you can put your queries on the chat box.
No questions.
Okay, madam. I think it's fine.
I think so. Not still question has not been asked. I think so.
Oh, mostly on this field, maybe the number of participants is less, or maybe is not working on this field.
Okay, so I would like to thank Dr. Sharma for his enlightening talk on vibrating sample magnetometer techniques. He covered what is magnetics and what is magnometric technique, how to use and analyze the results. Thank you very much, sir, for sharing your knowledge with us
Thank you,
and
madam.
sparing your valuable time with us. Thank you so much. I hope
Thank you,
we'll
madam.
be in touch with you and have you for future endeavors of us.
Yes, ma'am.
Thank you very much, Dr. Sharma, for.
Okay, okay, sir.
Thank you.
Thank you, thank you, thank
Thank you.
you,
Thank you, sir.
thank you, thank you.
Good afternoon, everyone. I once again, Rinku Bhatia, welcome you to 1 week national workshop on advanced synthesis and characterization techniques organized by Amity School of Engineering and Technology, Amity University, Madhya Pradesh. So for this session, we have with us Dr. Mansi Ghosh, who is Assistant Professor at Department of Physics, MMB, Banaras Hindu University, Varanasi. So before moving on to a session, let me introduce her to you all. Dr. Mansi Ghosh, as I've said, is Assistant Professor at Department of Physics, MMB, Banaras Hindu University, Varanasi. She has completed funded projects as well as ongoing projects to her credit. She has completed SERB DST project of which is worth more than 43 lakh and UGC startup grant of more than 6 lakh. Her ongoing projects include SERB power grant of more than 60 lakhs and IOE VHU grant of 11 lakhs. She has total international journal publications of more than 54 numbers to her credit and number of publications in national and international conferences. She is Executive Council member of Nuclear Magnetic Resonance Society of India, and she has also received number of awards. Professor S. Subramaniam Award 2023 from National Magnetic Resonance Society of India. Most Productive Researcher Award 2020 from Banaras Hindu University. Gati Nasi Award 2022 from DST. She is an thorough researcher and academician. So now I would like to invite Dr. Mansi Ghosh for a talk on nuclear magnetic resonance technique. Please, ma'am.
Thank you. Thank you very much, madam, for your kind introduction. And I am really thankful to the organizer for giving me opportunity to say basic NMR and some of its application. So basically, before 1945, we came to know about nucleus for the and bombard material with high energetic particle which is coming out of the accelerator, and for doing so we need big arrangement. But in 1945, Parcel, Torrey and Pound, they just observed experimentally that the radio frequency signal coming from works. And almost Bloch, Hansen and Packard, they also have observed radio frequency signal coming from water. So these two experiments basically are to the field, basically nuclear magnetic resonance. It is not just an instrument like XRD or any other spectroscopic measurement. It is a field of research. And so far, there are 5 Nobel laureates in this field of research. So basically, what is the basic setup of this? You all know that the nucleus has 4 properties: charge, mass, and its spin and the magnetic moment. So due to the existence of spin and magnetic moment, we can imagine nucleus as a bar magnet. So in absence of magnetic field, all bar magnets are randomly oriented along all possible directions. But when we place it in presence of a magnetic field, suppose our strong magnetic field is along z direction, then what happens? There will arise a magnetic moment, net magnetic moment along the direction of magnetic field. But to measure that magnetic moment, we have to bring this magnetic moment from z direction to the xy plane, that is at a plane which is perpendicular to the strong magnetic field. And for doing so, we have to apply RF field. That RF field magnitude is much lesser than the magnitude of our static magnetic field, that is 10 to the power 4 times lesser than this, and its frequency is same as that of the Larmor precision frequency of the nucleus which we want to probe. And like this way, just applying strong magnetic field, RF field, and we have a coil, and that same coil is act as a transmitter of RF pulse as well as receiver of the signal which is coming out of the compound. So with this type of simple setup, we can probe nucleus from 1945, and this is the field of nuclear magnetic resonance spectroscopy. So basically it has application almost all branches of science. These are the application of simple one-dimensional spectroscopy in pharmacokinetic measurement, metabolomics to identify the determination of the dynamic process and the protein-ligand interaction, MRI imaging, investigation of the structure and dynamics of protein and drug, and the quantitative analysis of a mixture of compound, purity analysis, and we can also identify an unknown compound. So this, and it has application almost in physics, chemistry, biophysics, and biochemistry. Even the medical field, it has application almost all branches of science. So far we can see that, you know that spin, basically by nuclear magnetic resonance spectrometer, we can observe the signal which is coming out of the nuclear spin. Nucleus is at the core of the atom. So basically that signal is coming from the nuclear spin. So experimentally first, by Stern-Gerlich experiment, we know that electron spin exists, and in 1943 he got Nobel Prize. In 1944, Rabi, he gave the idea that it is possible to measure the magnetic moment which arises due to the nuclear spin, and that magnetic moment can be measured by using a static magnetic field and the RF field. That idea, that concept was given by Rabi for that. And 1945, those two remarkable experiments by two independent scientists, Bloch and co-workers and Purcell and co-workers, because of they found that radio frequency signal are really coming out of paraffin wax as well as water. And in 1952, they got Nobel Prize. In 1991, Richard Ernst, he basically designed lots of NMR methodology for observing the structure and dynamics of biomolecule. And he is the just father of high resolution NMR. And he got Nobel Prize in 1991. In 2002, Kurt Thich, he got Nobel Prize due to just explaining the structure as well as dynamics of biomolecules, especially the protein structure. And 2003, Lutterberg and Peter Mansfield, they also obtained Nobel Prize for discovering MRI. Basically, the basic of NMR and MRI are same. So you can see that first you start from the physics. Basically, physicists are the give birth to this field NMR, and then it goes to chemistry people, and now its most application is in medical science. So basically, for each and every range of the electromagnetic wave, you can see one of the spectrometer that is called gamma ray. It is Moisbar spectroscopy, but I want to say that gamma ray means here it is the transition between the nuclear energy state, and that energy state is mega electron volt range. And X-ray is the XRD, X-ray absorption. It's basically the excitation of core electron. And UV visible, it is the transition between the electronic states. Infrared, it is the transition between the vibrational state. And EPR is the basically electron paramagnetic resonance, by which we can probe the electron spin, and it falls in the microwave region. And radio frequency, RF radio frequencies region, it is the nuclear magnetic resonance spectroscopy. So its energy is less and frequency is also less. And it is a non-invasive technique. Then basically what happens by the application of RF field? In presence of static magnetic field, those nucleus which are basically act like a bar magnet, they have a magnet, they are associated with a magnetic moment, and the energy is minus mu dot B. So in presence of the static magnetic field, it is just some of the nucleus, it will precede along the direction of the magnetic field, and some of the nucleus, it will precede along the opposite direction. But as this direction, that means when the magnetic moment is parallel to the magnetic field, it's energetically more favorable because its energy is lower, minus mu dot B, that means B mu 0, its energy is lesser than the energy when it is anti-parallel to the magnetic field. That's why more number of nuclear spin will align along the direction of the magnetic field, and we will get a net magnetization along that direction. And by the application of RF pulse, it just transit from just spin flip transition, it's spin up to spin down state, or spin down to spin up state. So this is and by the application of RF pulse, here this is the picture of free induction decay, and the dwell time, it is basically measured the time period between two data point. This is the FID in NMR, or FID basically it is the kind of signal we are getting through the NMR spectrometer. So far, what is the basic arrangement of the NMR spectrometer here? First of all, in the absence of strong magnetic field, all the bar magnets are randomly oriented, and there is no magnetization along any direction. It is the totally isotopic distribution of nuclear spin. When we apply a strong magnetic field, we will get a magnetization along the direction of the magnetic field, that is along Z direction. And if we apply a RF field along the x-axis, then what happens in 90 degree, actually basically we are applying 90-degree RF pulse for very certain duration, maybe in the order of microsecond or millisecond range. So this 90-degree pulse, it brings the magnetization from the direction to the XY plane. And once we just turn off the RF field, what happens? This magnetization will always try to go back to its equilibrium position, because equilibrium position is along the direction of the magnetic field. So there will be a change in the magnetic field in the XY plane. The change in the magnetic field will induce an EMF. And the induced EMF, basically, we are measuring as a signal of FID. And if we just transfer this signal, that is the time domain signal, in the frequency domain, we will get the NMR, just a resonance line. So that is the basic setup of NMR spectrometer. Now, we can say that why this technique is so unique than any other device. So first of all, it is a non-invasive technique. The sample which we are using, that amount of sample, it's remain intact. Even after performing your experiment, you can just collect the sample in its pristine form. There will nothing happens with your sample. And second thing is that you can selectively probe. Basically, suppose in your compound you have carbon, 13, nitrogen, oxygen, and phosphorus, and other elements. So you can selectively just probe each and every nucleus within your sample. And you can get signal, or you can get the structure of the compound at different physical conditions, like different pH, temperature, and by using different solvent, by applying different amount of pressure on it. And most important thing is that for glass compound, it is not possible to get the structural determination of glass by XRD is not possible. So basically, solid state NMR is the just essential device for the quantification of this glass material. So how can we do quantification? Suppose in your silica, there are different Q species, Q0, Q1, Q2. So accurate amount of Q0, Q1, Q3, Q2 species, it is possible to quantify by NMR measurement. And we can also perform NMR experiment in solid, liquid, gas, and gel form. And this is the most important thing, is that in XRD, yes, if you can make a single crystal of your compound, then you will get very nice information by single crystal XRD measurement. But you cannot get information about the dynamic of the system. So due to the existence of intrinsic time scale, like spin lattice relaxation, spin relaxation time, we can just probe the structure as well as dynamics of a compound by using NMR spectrometer. So this is just a cartoon which says that just by tuning your radio at a radio frequency range, you can listen the music which is coming from the far distance. Similarly, you can listen the music which is coming from the core of the atom by tuning your RF field at a frequency which is equal to the Larmor precision frequency of a particular nucleus. So this is by NMR spectrometer, the spin and magnetic moment. These two are basically less tangible quantity of a nucleus, because the value of spin angular momentum of nucleus, that is spin angular momentum, magnetic moment which is arising due to the spin value, that is mu equal to gamma into S. What is gamma? Gamma is the gyromagnetic ratio, that is E by twice M. As mass of the nucleus is much greater than the mass of the electron, so the spin magnetic moment of nucleus is much lesser than the electron. So this magnetism and spin, these two properties of the nucleus, these are less tangible. Neither the physical nor the chemical property of the material is responsible for the spin and magnetism of the nucleus. But due to these two properties, we, those people who are interested to probe the nucleus, we are getting opportunity to probe the matter, and we can get the information about the structure and dynamics at atomic scale resolution. So this spin and magnetism are very important for those who are dealing with NMR spectroscopy. Now, if I ask that what is spin, can anyone answer me what is spin? Hello, are you listening me?
Yes, ma'am, you are audible.
Yes, I'm audible. So can any student answer me what is spin? What is your concept about spin?
Yes, students, you can answer through chat box.
Okay. So basically, spin is such a quantity which has no classical analog. Classically, say that is the analogy of spin, as from our childhood we are just listening, that something which is just spinning like this way, that is spin. Basically, spin is also a angular momentum, like orbital angular momentum, but orbital angular momentum arises due to the mechanical moment. Okay, this movement of the electron and nucleus about a certain orbit. But this spin, it is such a angular momentum that is basically the intrinsic property. Even at an absolute zero temperature, you will this as nucleus as well as electrons, they have this property, and due to this spin there arises a magnetic moment, and that magnetic moment is mu into gamma j. Here, if the j is the spin, then the magnetic moment due to this spin is mu. And you know that due to this spin angular momentum, there arises a magnetic moment, and when we place this bar magnet in presence of a magnetic field, it will experience a torque. And that torque is basically rate of change of angular momentum, right? And as the angular momentum and magnetic moment are related by this relation mu equal to gamma into, just put this value of j here in this equation, you will get this equation. So this is very important equation. You may ask me question that why we are always picturize spin, angular momentum, and spin magnetic moment, that is mu, is it is always spinning around the magnetic field. Why it is spinning? What is the reason? So you can get this answer from this equation. See, our rate of change of magnetic moment should be such that it always should be perpendicular to mu as well as h. Okay. So if this change in the magnetic moment, which is along that direction, if it has to change with the time in such a way that it should be perpendicular to both this mu and the b, then its direction will be just tangent to this circle, right? So that's why it is always precesses around the magnetic field. Whenever you place a bar magnet in presence of magnetic field, it started to precess, and that is called the Larmor precession. And the frequency at which it is precesses around the magnetic field, it is called Larmor precession frequency. And this Larmor precession frequency basically proportional to the magnetic field. If you increase the magnetic field, the Larmor precession frequency will increase. And this spin, basically, it is in classical world, there is no existence of spin, and it has some weird properties. Just telling you in very short term that suppose you have a nuclear system, nuclear of spin half, And you like to measure that how many nucleus are in along the positive direction of the z-axis. Then you will find half of the nucleus will be along the positive direction and half of the nucleus is along the negative direction. Basically, it says not the exact value, but the probability. So probability of finding nucleus along the positive direction is 50% and probability of finding the nucleus along the negative direction of z-axis is also 50%. Now, another thing is that suppose you have spin 1 nucleus and you want to measure the same, that the number of nucleus or percentage of the nucleus along the positive direction. So if you measure mu z, you will find this type of things, that half of the, 33.3% nucleus is along the positive direction of z-axis, 33.3% along the negative, and 33.3% is just not aligning along positive or negative direction. So basically, what we can predict by classically quantum mechanics say this in terms of the probability. And suppose you have spin along the positive z direction initially, spin half nucleus, and it is aligning along the direction of z-axis. And you measure mu x, that is the number of nucleus along positive and negative direction of x-axis. Then you will also get the 50-50% probability. Similarly, again, if you measure your spin, when spin align along the positive direction of x-axis, and you like to measure how many nucleus are in positive and negative direction of z-axis, then you will also get that 50-50% probability. It says that basically it always like to give you the state value. That means it forget all about its history. It's always give the probability of its current state. And here, actually, these things is very important in NMR because we frequently use pi pulse or pi by 2 pulse. So initially, if your magnetization is along the z direction, positive z direction, and if you apply pi pulse along the x direction, then all of your spin will align along the negative direction of the z-axis. And the probability of getting nucleus along the positive direction of z-axis will be 0, because here we are applying 180-degree pulse. Similarly, instead of applying 180-degree pulse, if we apply 90-degree pulse along the x direction and measure mu z, then we will get 50-50% probability of having nucleus along the positive and negative direction of z-axis. And here also, if we just apply pi by 2 pulse along the x-axis and measure the probability of getting nucleus along the y and minus y direction, then you will get that along the minus y direction, this is the 100% probability, and positive direction of y-axis, it is not possible. That means 0% probability. So this is the probability of outcome. And classically, if you think like this way, that z direction, it is along the z direction, you apply then 180-degree pulse, it just directly come downward. That means from z to minus z. So this is also what we can just guess classically quantum mechanics gives in terms of the probability. Basically, we measure the spin value in complex space, not in the real space. And this is basically the quantum mechanical form of the angular momentum operator. This is spin angular momentum or orbital angular momentum, any kind of angular momentum operator. They are following these things, and they are also following this cyclic commutation relation. Now we will discuss that, that from Riemann splitting, that the selection rule. So here in case of NMR also the nuclear spin also follow the selection rule. So selection is also plus minus 1. So first of all, if we consider just single nuclear spin, then it may align along the negative or positive direction of the static magnetic field or negative or positive direction of the z-axis. So the energy that is beta means it is the spin down and it is spin up. So actually, basically in NMR, any book of NMR, you will get the symbol alpha and beta. Alpha means spin up state and beta means it is spin down state. So whenever there will occur a transition from the spin up state to spin down state, you will get this absorption spectrum. That is for the single nucleus spin, and the energy difference is, this is our Larmor precision frequency, mu01. Now, instead of this single spin system, if we have coupled system, that means when we are just considering two nucleus. So two nucleus, it may be both of the nucleus are parallel to the external magnetic field. It may happen that both of the nucleus can align along the opposite direction of the magnetic field, and one of the nucleus aligning along the positive. You can consider nucleus 1, that is first and second, and nucleus 2 is in along the opposite direction of the magnetic field. So this, when it is that photon, when the both nucleus are same type, that means not photon carbon, only photon, then the energy of these two states, that is alpha beta and beta alpha, it is same. And beta beta state and alpha alpha state, their energy are different. In this case, what should be the energy level? Energy level will be like this: M1 nu01, M2 nu02, and M1 M2 J12. J12 is the coupling energy between two coupled spin. So by this type of so transition will occur from 1 to 2. This is 1 to 2, 1 to 2 here. That means alpha alpha state to alpha beta state, and transition allowed transition can be 3 to 4. This is 3 to 4, and 1 to 3, and also 2 to 4. These are the allowed transition. These 4 are the allowed transition for these two couple spin, and this is the energy. So this is basically for single quantum transition. Basically in NMR, single quantum transition is you will get in general 1D experiment, but it is also possible to observe the multiple quantum transition. That is, delta M can be plus minus 2, plus minus 3, that is double quantum transition, triple quantum transition. It is also possible to observe by NMR spectrometer, and that kind of experiment, you have to design it in 2 dimensions. And that is also possible, and that's why we can say that by manipulating the spin, we can observe those transitions which are not possible to observe in any other spectrometer. And similarly for this three couple spin selection rule will be like this, that delta M plus minus 1, and another rule is that among these three couple spin, only one spin can do spin flip transition. That means here, see this alpha alpha alpha, only this middle one, it can change its direction from alpha to beta. And here also the first one can change the direction. And if you just go from here to here, only this first one can change the direction. So these are the selection, these are the energy level for three couple spin energy level, and it is the selection rule is that delta M plus minus 1. That selection rule is for single quantum transition, and another other selection rule is that only one spin can change its direction. So these are the possible transition for three couple spin, and also for three couple spin, double quantum transition or multiple quantum transition are possible. These are the example of double quantum transition. It is from alpha state to beta alpha state, and the frequency is this, and it is possible to observe this signal also by NMR spectrometer, but you have to select this path that by applying the RF pulse in a nice order and by applying NMR methodologies, and this type of experiment will give you lots of information. And this is a very nice book that is called Spin Choreography. Basically, by applying RF pulse or by playing with RF pulse, you can give the direction to the nuclear spin, that how the way it should dance. So this, you can follow this book. This is a very nice book. Now, those are the basically these nuclears. It is routinely we perform experiment on those nucleus. It is really easy to get signal, that is photon, lithium, sodium, barium, carbon-13, fluorine, aluminium. Frequently, we perform experiment on this. And difficult and challenging nucleus, these are actually quite activity as well as the gamma value. It is sometimes problematic to get the NMR signal. So these things I already have explained you that what is the basic of NMR. Now, classically, if I have to explain that, how classically we can explain that magnetization which arises along the Z direction, it is possible to bring it along in the XY plane just by applying a RF pulse. What happens when we apply magnetic field, very strong magnetic field along the Z direction? There arises a net magnetization along Z direction, and the nuclear spin magnetization will precede at a certain angle along the direction of magnetic field. And if we apply B1, then what happens? The effective magnetic field in this case will aligning along this B effective direction, which makes a certain angle with that of the Z direction. And this magnetic field B1, it is always changing its direction because it is the changing its direction at a frequency which is equal to the Larmor precision frequency of the nucleus. So when it changes the direction from positive direction of y-axis to the negative direction of the y-axis, what happens? This angle, the angle of the cone at which it is preceding, that angle is big, angle become the greater angle. So from acute to it become obtuse. Then again, if we change the direction of B1, the angle is again, it become wider. And finally, it comes to the XY plane. So classically, we can explain that by applying RF field, which is at the frequency of the nucleus, it is possible to bring the magnetization which arises along the Z direction, from Z direction to the XY plane. Now, things is that, yes, we bring magnetization in the XY plane. Then what happens? By applying, suppose by applying 90-degree pulse, we bring magnetization from Z direction to the XY plane. Then all the spin again start to precede in the XY plane, and this phenomena will be just like this. That is just randomized. You cannot get any signal. Then why? What happens? How can we get signal? Basically, whenever we are bringing this magnetization from Z direction to the XY plane, there arises a correlated phase relationship among all the spin. All the spin means you have to just imagine approximately 1000 spin. So 1000 spin is phase is such that they are correlated to each other, and that is called coherence. There is a correlated phase relationship. There arises correlated phase relationship among all the spin which we bring from z direction to the xy plane. So how can we get that idea of correlated phase relationship? And that is kind of the Mexican wave. Mexican wave, what is this? In football ground, if one spectator is just stepping up and down, then you cannot see any observable wave that it is just throughout the stadium. But if there is a correlation of the movement of all the spectators of the football stadium, then you can feel that as if one wave is passing. So this is a very small example. Here you can see that all these people who are just standing like this way, there is a correlated phase relationship among the movement of all these people, and you can just feel that a wave is passing like this. And another example is like this, that when there is a correlated phase relationship among all the spin within the compound, as if spin wave is passing. And when this type of correlation, so NMR signal basically arises due to the development of coherence among all the spin. Coherence means correlated phase relationship among all the spin within the system. Now, how the way this correlation is getting destroyed? See, you can imagine that this RF pulse basically not imagined within the system, and we apply this perturbation for a certain duration, maybe of the order of millisecond or microsecond order. Then what happens after this? When we withdraw this perturbation, that means when we remove the perturbation from the system, what happens? This system will again try to go back to its equilibrium position, right? And the equilibrium position, it can go back, sorry. It can go back to its equilibrium position by two mechanisms. One is spin lattice relaxation, another is spin-spin relaxation. What is spin lattice relaxation? When the nuclear spin just exchange energy with the surrounding media, that is lattice, and go back to its equilibrium position, then it is called a spin lattice relaxation. And when the nuclear spin, they are exchanging energy among themselves. That means that nucleus, which is in the excited state, it exchange energy with that nucleus, which is in the ground state. And this type of relaxation, that means this, in this mechanism, this nuclear spin also can go back to its equilibrium position. And that is called the spin relaxation. So these two things, that spin lattice relaxation and spin-spin relaxation, these two are the intrinsic time scale of the nuclear spin system. And due to the existence of these two intrinsic time scale, we can get the idea of the dynamics of the molecule. Okay, so basically, what is the basic reason of this destruction of the coherence? Why coherence is destroyed? Coherence means correlated phase relationship is developed. Then question is that why it is destroying? Because of the existence of local magnetic field, local fluctuating magnetic field. What is this? What is the source of local magnetic field? You apply RF field and you apply the static magnetic field. Then what are other field, that is local magnetic field? Basically, this local magnetic field arises due to the orbital angular momentum of electron, spin angular momentum of electron, and the spin angular momentum of nucleus. So our nucleus is basically inside a molecule and it has its surrounding. Okay, so these surrounding are basic reason of this local magnetic field which arise at the position of the nucleus. And why this local magnetic field is fluctuating? Because of the translational, rotational, and vibrational motion of the molecule. Basically, in solid, it is the rotational and vibrational motion of the molecule. So due to the rotational and vibrational motion of the molecule, magnetic field which just arise at the position of each and every nucleus within the system, that local magnetic field basically different for different nucleus. That's why the phase is also different. Phase is basically represented by this quantity there. That phase is also different. So when the phase is getting changed, there will be no correlation. Okay, and like this way, the correlation is getting destroyed. So basic reason for this spin lattice and spin-spin relaxation is the fluctuating local magnetic field. Now, question is that how can we get idea about the molecular motion just by measuring the spin lattice and spin-spin relaxation time of the nucleus? This diagram, this is very important. It says that, what it says, that when your molecular motion, that means when the molecular motion is very fast, that is the correlation time. When molecular motion is very fast, means the correlation time of the molecule is shorter than the Larmor period. Then this frequency of the local fluctuating field, it is of resonance with that of the Larmor precession frequency. So when it is of resonance, that means this mechanism, it does not influence the mechanism of relaxation. That's why the spin lattice relaxation time is very large when the molecular motion is very fast. And at the same time, when the molecular motion is very slow, that means this correlation time is much longer than the Larmor period. Here also, it is also of resonance with respect the local fluctuating magnetic field is of resonance with that of the Larmor precession frequency or RF field. Then when it is in the of resonance position, it also cannot influence the mechanism of relaxation. When the molecular correlation time is closely to the value of the correlation time, only then the relaxation time is the lowest. That means in this case, the molecular motion can influence the relaxation mechanism. So this is true for the spin lattice relaxation time. For spin relaxation time, what happens after when the molecular motion is very slow, it behaves like a rigid lattice, and the spin relaxation time will become almost constant. So that's why by measuring especially this spin lattice relaxation time, we can prove the dynamics of the system. If you have any question, you can stop me and ask me your queries. So this is the important parameter, that is relaxation, and how can we prove the dynamics of our molecule or the compound of our interest by using NMR spectrometer. Now, question is that I told you that just by manipulating RF pulse, see, it is not possible to manipulate the static field. You cannot put your hand there because it's very strong magnetic field, and we use the superconducting to achieve that 11.74 Tesla magnetic field. So you cannot touch that field. Just by playing with the RF field, that spin choreograph RF field, you can manipulate spin and you can give direction to the spin, that how the way it should dance. So why? Now question is that why only we can influence the RF field, and how by just manipulating RF field we can do that kind of things. So basic answer is that in the rotating frame of reference, there is no existence of the static magnetic field. In rotating frame of reference, only the RF field is exists. Why? How can you say that? This equation I already have explained you that rate of change of magnetic moment is equal to mu into gamma H, mu cross gamma H. And this equation is also very basic equation of those who are basically from physics background. What this equation says? It says that rate of change of a vector with respect to the laboratory frame is equal to the rate of change of the vector with respect to the rotating frame plus this gamma is the frequency at which the rotating frame of reference is basically rotating with respect to the laboratory frame, and F is your vector. So this equation is very familiar to us. And why we are discussing this? Because our nuclear spin about which we are talking, our nuclear spin is always persisting around the magnetic field. That means it is in the frame of rotating frame of reference. And we are observing it by sitting at the laboratory frame. So we must have to consider this equation here. Instead of this equation, d mu dt equal to mu cross gamma H, we have to consider this equation. Just by simply putting F equal to mu here in this equation, you will get this equation. That is delta mu, delta t. Delta mu, delta t is equal to mu cross gamma H plus omega. So here only one quantity is added here. These two equations are more or less similar, only the effective magnetic field in this case is H effective equal to H plus omega by gamma. That is the effective magnetic field. Now, here we apply Z along the Z direction, we have our static field, and along the X direction, we have our RF field. So our effective field is mu H0 plus H0 minus gamma omega by gamma plus H1I. This along the Z direction, and these things is along the X direction. Now, this omega, we have to choose the radio frequency signal or radio frequency such that this omega should be equal to gamma into H0. When the omega is equal to gamma into H0, then this part will vanish and effective magnetic field will be H1 into I. That's why when this rotating frame of reference, our nucleus always experience the field which is equal to the RF field. Now, why certain nucleus are very sensitive and you will get signal very easily, and certain nucleus it is very difficult to get the signal. See, for proton, its natural abundance is 100% and its gyromagnetic ratio is also very high. Suppose when we are talking about the 500 megahertz spectrometer, basically in NMR, we are using this type of basically symbol. We are saying that it is 500 megahertz spectrometer. 500 megahertz spectrometer means at this magnetic field, the Larmor decision frequency of photon is 500 megahertz. Okay. So these all values are with respect to the 500 megahertz spectrometer. And here for carbon-13C, we only can see the NMR signal from those nucleus which has a definite spin value. If its spin is 0, see carbon-13, its natural abundance is very, carbon-12 natural abundance is very high, but its spin value is 0. That's why you cannot observe the signal of carbon-12. We can observe carbon-13, but its natural abundance is 1.1%, and its gyromagnetic ratio is also 4 times lesser than that of the photon. Fluorine signal, yes, it is possible to see it, and it's very easy to, maybe within 10 minutes we will get the signal, fluorine signal, and phosphorus also. So it basically, the sensitivity of NMR signal, it depends on the natural abundance as well as the gyromagnetic ratio. And those nucleus whose spin value is half, it is easy. And for those whose spin value is greater than 1 or 1, there is, for that kind of nucleus, there are this quadrupole moment, and due to this quadrupole moment, there will arise a broadening of the signal, and it is difficult to get that kind of. So this chemical shift, after the discovery of NMR spectrometer in 1945, another important discovery is the chemical shift. So what is this chemical shift? Chemical shift is basically, it says that the magnetic field experienced by a particular nucleus is not exactly equal to the magnetic field what we are externally. Suppose you are applying external magnetic field 11.74 Tesla in your 500 megahertz spectrometer, and you are probing nucleus 13C. It cannot experience that field. Why? Because the nucleus is surrounded by the electron cloud, and the electrons are always revolving. And you know that when a charge is revolving surrounding a nucleus, it generates a secondary magnetic field. Okay, or it is sometimes called the induced magnetic field. And the direction, this secondary magnetic field, its direction depends upon the orientation of the molecule. Sometimes it is added with the external magnetic field, and sometimes it along the opposite direction of the external magnetic field. So it should be plus minus be induced. So local magnetic field or effective magnetic field in experienced by the nucleus is basically B0. B0 is the externally applied magnetic field, plus minus B induced. So this induced magnetic field, it arises due to the revolution of electron cloud surrounding the nucleus. And the value of this induced magnetic field, it is also proportional to the external magnetic field. We increase the external magnetic field, the induced magnetic field it also increase. So it is basically says that induced magnetic field is equal to sigma into B0. Okay, plus minus sigma into B0. This sigma is the chemical shift anisotropic tensor. It is second rank tensor. Basically, it is a second rank tensor. Now, why it is so important? It is important because if we just probe this value, you can say that what is the local surrounding of the nucleus. See, these three are carbon. All three are carbon, but their locality is different. Their chemical bonding and their local electronic environment, local chemical surrounding are different. That's why we are getting three different signals here. And similarly, if we probe the oxygen instead of carbon, then you will get different signal here at different place. That means their Larmor Piston frequency will be different. That's why it makes NMR spectrometer is unique from any other spectrometer. It gives you the information about the local surrounding of a nucleus. And we measure the chemical shift by this, that we always measure chemical shift with respect to a certain molecule. For carbon 13, we use TMS, trimethylsaline, and we measure it like this way. This is the equation. And you will get in library, you will get these things that here you see that when the shielding is more, shielding means the nucleus is getting shielded by the electron cloud. When the shielding is more, your chemical shift will be less. See here at 185.4 ppm, chemical shift is 0. And when the shielding will be less, chemical shift will be more. That means chemical shift will move to the higher frequency side. So in library, we'll get the idea for different group, chemical group, the chemical shift will be different.
Yes, ma'am. Any issue, ma'am?
Issue means it is not moving. I'm just checking. First
No,
time stop
you are
sharing.
You are audible. Now
Yes,
it is
yes.
not. Now it is not
Okay.
visible. Now your screen is not visible.
No, I just actually stop it.
Okay.
So can you see the screen now?
Yes, it is visible. Correlation
Acha.
between chemical shift and
But
chemical
it is
shifting.
not moving. I don't know why it is not moving.
Okay. It's not moving.
Yes.
Now, yes, now
Okay.
it's moving.
Now see, this is for the cholesterol. This is a big molecule. It has maybe 22 or 25 carbon. So for 25 carbon or 26 carbon in different chemical surrounding, you will get signal at 26 position. And see here, the chemical shift, it varies from almost 0 to 150. Okay, so same carbon nucleus deciding at different chemical environment, different its local surrounding electronic distribution is different, and that's why for same carbon nucleus, for certain nucleus, this chemical shift is nearly 150, and for certain nucleus, the chemical shift is nearly 0. Then what factor just affect the chemical shift? So there are lots of factors. I will discuss few of these factors. That is inductive effect, hybridization of the carbon, magnetic anisotropy or resonance effect, and the ring current effect, steric effect, and hydrogen bonding. So what is inductive effect? Suppose you want to probe the proton, and proton it is bonded with carbon. You know that carbon is more electronegative than proton. Then what happens? This carbon will attract the electron cloud surrounding the proton nucleus, and this proton will be deshielded. Deshielded means its chemical shift will shift towards the higher frequency. And with respect to this carbon, the chlorine is more electronegative. And if you want to just probe the carbon, then you can also see that its chemical shift is shifted towards the positive direction. That means towards the higher frequency side. And here, from this chart, it will be more clear to you that silicon it is considered as electropositive. So when it is attached with the silicon, we consider that chemical shift is 0. And again, if it is this group, CH4, it is attached with the proton, its chemical shift is 0.23. When it is attached with the iodine, it's just slowly it is increasing, because this bromine is more electronegative than iodine, and this chlorine is more electronegative than chlorine. So you can see that as it attached with the more electronegative atom, and this electron cloud surrounding the proton is getting attracted towards the electronegative atom, and this proton is getting deshielded, and its chemical shift is getting shifted towards the higher frequency side. So if you just observe this from silicon to fluorine, it's gradually increasing. So this is the inductive effect. And not only inductive effect not only depends upon the electronegative atom, but also the structure in which this electronegative atom is residing. Another thing is that your hybridization, if it is in the sp2, sp3, or sp or hybridized state, then chemical shift value will also be different. This is also very important, that is shielding effect, magnetic shielding. What is the reason? Whenever there is a pi electron, what happens? The pi electron is moving. So when it is moving, it also induces another magnetic field. Actually, initially that chemical shift which arise, this is basically the sigma electron, which is bonded with the nucleus. And pi electrons, for pi electrons, if it's moved in the along the direction of the along the clockwise direction, its magnetic field will be along certain direction, and if it's moved along the opposite direction, anti-clockwise direction, then its magnetic field will also be along the opposite direction of the magnetic field. So which region will be shielded? Shielded means nucleus will be more shielded and less shielded. It depends upon the direction. That is basically carbonyl group carbon. And if your proton is here, suppose your proton is here, then it will be de-shielded. And if your proton is residing at this region, it will be shielded. So chemical shift of the proton for this type of proton, when the protons are along that direction, then it is 7 to 8 ppm. And when proton reside in this plane, its chemical shift is 2 to ppm. So same molecule, certain direction, that's why it is called the anisotropy. Certain direction it is shielded, certain direction it is de-shielded. And if proton resides, here we are talking about proton because basically we are measuring the chemical shift of proton. And here, in this case, when it is along this direction, protons, then it is 2 to 3. And when protons are along the de-shielded region, its chemical shift is 7 to 8 ppm. Similarly, for acetylene is this 3 bonds, actually triple bond symmetric molecule. It also, these pi electrons are moving and it generates a magnetic field. It is along, if it is in this plane, it is along the direction of the magnetic field. That means it will be de-shielded, and if it is along the opposite direction, it will be shielded. Similarly, actually it also depends at what position your proton is with respect to this pi bond. Here, see these two molecules, basically they are sister molecule of each other. But due to the existence this pi bond, here you can see that this proton, this chemical shift is 0.99, and for this proton it is 1.63, and similarly here also it is 1.10 and it's 0.85. So chemical shift varies. It also, what should be the value of chemical shift? It also depends on which direction it is with respect to the pi electron. And the same thing is for carbonyl group, alkyne group, and other this type of shaped molecule. Actually, this type of molecule which basically don't have any symmetric direction. For that kind of molecule, you can observe this magnetic shielding and de-shielding effect. And ring current. Basically for benzene ring, pi electrons are moving like this way, and it induces a magnetic field, another magnetic field. And due to this magnetic field, certain region, it is shielding along this direction, it is shielding, and that direction it is de-shielding. So if you just measure the chemical shift of this carbon, it will be shifted towards the higher frequency side, and if carbon reside in this plane, then it will be shifted towards the lower frequency side. Same thing here, also you can observe that in this case it is 2.34, and it is when it is just connected with the electronegative oxygen, it's become 2.58. This is very important thing. This is the very good example of shielding and de-shielding due to the ring current. See, these 6 photons, if you measure the chemical shift, it is minus 1.9. That is, this region is highly shielded. And this nucleus, this 12 photon, which are at the exterior part of this aniline, its chemical shift is 8.2 plus 8.2 ppm. So this region is deshielded, highly deshielded, and this region is shielded. And same thing, same type of difference in chemical shift may arise for not only for pi electron but also for the sigma bond. And mesomeric effect or resonant effect, what is this? This is that the double bond, whenever there is a double bond, that is pi electron, and due to the just attachment of various group, some group positive resonance effect, that means some group can give electron to that group. This is the example. Just take this example. This is ethane. Here for all 4 protons, the chemical shift is 5.29. Now when it is attached with this ketone group basically attract electron from this molecule. Then what happens? It will get deshielded. Deshielded means its chemical shift will be shifted towards the higher frequency side. It becomes 6.52. And when it is attached with the methoxy group, what happens? Methoxy group basically pushes electron cloud towards the molecule, and it will be shielded, more shielded. More shielded means it. Okay, then the steric effect. See, this in R, this actually here you can basically these people, this community, they measured the O17 and 15N chemical shift. So due to this difference of different group, the existence of different group, how the way the chemical shift of this oxygen and nitrogen is getting changed, you can get this data here. So these A, B, C are basically this group which are attached with this molecule, and how the way it is getting changed. And not only due to the existence of various group, but also the conformation of the group. When it is in the half-case type of conformation, and when it is in the chair conformation, you can see that from this data that this chemical shift also depends which conformation it is. That means basically the molecule is whether it is in chair conformation or half cage conformation, and which group is attached with the molecule. And that is also is one of the example for polysaccharide, and which molecules is attached. This basically this blue colored, it is attached with this polysaccharide, and you can see that value of both carbon chemical shift, it is getting changed. Here, this is the alpha carbon and beta carbon, its chemical shift is getting changed due to the substitution of different chemical groups with this monosaccharide unit. And hydrogen bond also designed, because due to the existence of hydrogen bond, there arises a polarization. Polarization means along certain direction, the distribution of electron cloud will be different, and chemical shift arise due to this factor. And this hybridization we already have discussed, and this type of actually library data you will get, and basically those people who are doing organic chemistry, they are using this type of data, because this says that which group it is. Basically for CH2, it's these all measurement are with respect to TMS. So for CH bond, it mainly arises from 4 to 5 ppm. For aromatic, those protons which are residing on the aromatic rings, their chemical shift varies from 6 to up to nearly 8.5. This type of data it is necessary to identify the group for the chemistry paper. Okay. Now, next important thing, first we have discussed basic element, then the relaxation, how we can measure the dynamics, and the chemical shift, in which way we can probe the local dynamics. See, you can see that chemical shift can may varies with the just involvement of electronegative atom, steric effect, involvement of various group with this, and the ring current, pi bonding, and the hydrogen bonding. Lots of factors it depends upon. So basically, this is also another discovery of NMR spectrometer, that is the Fourier transform spectroscopy. Richard Ernst, he got Nobel Prize, and he is the just father who gave this idea of Fourier transform NMR. So here basically basic things I'm just taking. Suppose you have to measure the frequency of a tuning fork. So one thing you can just do that, you just place your tuning fork by the side of piano and just pressing each and every key of piano. So for that key of piano, which frequency is same as that of the tuning fork, you will get a loud sound, and you can identify that that is the frequency of your tuning fork, and that is basically a continuous wave method. Okay, you are just scanning the entire signal, and you are getting, you can acquire the signal like this way by scanning various region. And another way to get the frequency of the tuning fork, you can just strike it, and you can record the time domain signal and can convert it and just do the Fourier transformation of the signal and can get the frequency of the tuning fork. So this FTNMR is that type of concept here. So basic difference is that FTNMR, the time of the acquisition of the signal is much lesser than the continuous wave. But for certain the compound, which is basically paramagnetic compound, we have to get the signal by this continuous wave method. Now we have already discussed the spin wave, spin relaxation and spin lattice relaxation time, and there are two ways to measure this. One is inversion recovery method. Inversion recovery method means first we apply 180-degree pulse and wait for a tau delay, and then we apply 90-degree pulse. So what happens? When we apply 180-degree pulse, the magnetization, which were initially along the z direction, is just transferred to the minus z direction. And whenever we are giving this tau amount of delay, this magnetization will try to go back to its equilibrium position. And in this time, if we apply 90-degree pulse, this signal, this magnetization will goes from this position to that position, and then you can apply a 90-degree pulse and measure the FID. And just by varying this tau value from low value to the high value, you can measure the value of spin lattice relaxation time. That is inversion recovery. Another one is saturation recovery. What is that method? So saturation recovery, basically we are applying 90-degree pulse repeatedly in very small duration. We are repeating 90-degree pulse again and again. What happens? It will reach the saturation. Saturation means the population of down state and excited state will be same. Then there will be no signal, and again but after certain delay, we are applying 90-degree pulse and measuring this FID. So this delay time, by varying this delay time, and we can just take 16 such data point and can fit and can get with the block equation and can get the value of T1. So T1 can be measured by saturation recovery, inversion recovery method, and how we can measure T2, it is the spin echo method. What is this method? Spin echo method is that first our magnetization is along the z direction, and we apply 90-degree pulse. We bring magnetization from z direction to the xy plane. Then what happens when we bring the magnetization from z direction to the xy plane? Suppose you are dealing with more than 1000 spin. So this spin, phase will be different. So slowly it will be phase out. Okay. Certain spin isochromat, it is called. Certain spin isochromat, it will move faster than that of the average spin isochromat, and certain spin isochromat, they are moving slower than the average spin isochromat. So as a result, it will slowly dephase out. So after certain delay, again we apply 180-degree pulse, then what happens? Those signals which are getting dephasing, it will again refocus or rephase along the opposite direction of y, that means along the minus y direction. That means we are getting as if a echo of the signal which initially was along the y direction, along the direction of minus y axis. That is basically the spin echo. So spin echo technique, we just apply 90-degree, wait for tau delay, and apply 180-degree pulse. So those spin which are dephasing out, they will rephase along the other direction. That is, initially if it was along the y direction, then finally it will arise along the minus y direction. So by this, we can measure the T2. Basically, for here you can, it is very nice explanation is that suppose during this tau delay time, what happens? See, we are just applying 90-degree pulse and wait for tau delay. It will try to dephase. And if we apply 90 degrees, suppose we are applying a mirror along the XZ plane, and this spin isochromatic, which makes angle gamma t with respect to y direction, it again make an angle gamma t with respect to minus y direction, and it will rephase along the minus y direction at a time 2 tau. Yes, so this says that once 90-degree pulse is turned off, the nucleus begin to dephase, net magnetization terms plane decrease, and the receiver direction signal will decay. And if we just apply 90-degree pulse, it again rephase in 2 tau time. So basically, CPMG method, it is just repetition of this spin echo at the interval of tau, 2 tau, 5 tau, 7 tau, like this. And we will observe the echo at a time 2 tau, 4 tau, 6 tau, and 8 tau. And we will get this type of signal. The question is that here, for the first time when it is just after first dephasing, when it is rephasing, it's all the spin, it is not possible for all the spin isochromat to dephase out. So slowly decaying. Okay, so at 2 tau, 4 tau, that kind of signal, it is decaying out. And if we feed scarf with magnetization, that is m equal to m0 e to the power minus t by tau, then we can get the value of T2 relaxation time. So during when we are measuring the spin relaxation time, there will be no surrounding, only the exchange of energy among the nuclear spin. And if we feed the exponential decay of the magnetization by the equation m equal to m0 of spin relaxation time. So this, it has a huge application in basically the imaging, neuroimaging, biomarker, orthopedics, and the renal imaging, liver imaging. It's medical science, it has huge application. I have already explained basically the difference of single echo and the CPMG method is that in CPMG method, we are repeating this 90-degree tau, 180-degree pulse in the different time scale. So this videography shows you just that how it can rephase, applying this tau, 90-degree tau, 180-degree pulse. And solid echo is basically for quadrupolar nucleus. Instead of this 180-degree pulse, we are applying 90-degree pulse. Now, I will explain little bit the difference between the solid and liquid state NMR. In liquid state NMR, due to the tumbling motion of the, how much time I have? Okay. Okay, madam, how much time I have? Hello?
Ma'am, you can sum up in
Almost
2
over.
minutes. Though we were supposed to finish by 4, but since we begin a bit later, so you can take another 10 minutes.
Okay. So basically, just in a nutshell, I will say the difference between liquid state and solid state NMR. In liquid state, due to the tumbling motion of the molecule, all the anisotopic, basically here, when we are talking about the nucleus, we have dipole-dipole interaction, and for more than half spin nucleus, it has quadrupolar interaction, and the spin lattice interactions, chemical shift anisotropy interaction, spin rotation interaction, and all these interaction Hamiltonian, it has a isotopic part as well as an isotopic part. So, but in liquid, due to the continuous tumbling motion, all the anisotopic term is cancelled out. And that's why life is very simple. For liquid state NMR, we need to be very sharp signal, and you can identify by seeing your library or by DFT calculation that which signal comes from which nucleus. And this is for the cholesterol. But, okay, I'm just coming later here. But in solid, we have all kind of interactions. So it is the broadening. Suppose we are trying to measure the, just trying to the get signal of 13C. So for 13C also, we have to apply certain method. First of all, okay, I'm just, sorry. Okay, so here, our Hamiltonian, we have spin part and facial part. Okay, so we can average the spin part by applying RF pulse, but the spatial part, we have to apply the magic angle spinning. What is magic angle spinning? See, all these interaction Hamiltonian, if we just go through this interaction Hamiltonian here, or I'm just showing you this. This term, 3 cos square theta minus 1, this is dipole-dipole. Basically, for photon, it is much bigger signal. In liquid, you will get sharp signal, but in solid, you will get broad signal because homonuclear dipole-dipole coupling. So if we just rotate our rotor, that means sample tube in solid at an angle which is 74.54 degree, then what happens? So if all this term, all the 3 cos square minus 1 term will be average out. That means this spatial term will be average out. And the signal will be just like the liquid signal. I'm showing some signal of liquid solid state signal by applying, that is 13C CP mass. Sorry. And another thing, it is the cross polarization. Cross polarization means we can transfer the polarization. See, for photon, you know, it is 100% abundance and its diamagnetic ratio is very large. And polarization means, polarization basically measures the population difference between two levels. We can transfer the polarization of photon to carbon. That is called cross polarization technique. How it is possible? Actually, by using double resonance probe, we can apply RF field to photon channel as well as the carbon channel. And when this Hartmann-Hahn condition is matched, that means gamma C DC equal to DC is basically the RF field at carbon channel, and gamma H BH When these conditions will met, the polarization of photon will transfer to carbon and sensitivity of carbon signal is increased. So basically in solid, we are applying magic angle spinning. Why it is called magic angle spinning? Because it is doing kind of magic, that is, it is that averaging the facial part and giving us a signal like a liquid signal in solid sample. Thank you very much, madam, for your time and patience. So if you have any question, please ask me.
Students, participants, are there any questions? Rinku ma'am, over to you.
Participants, if you have any query, you can write on the chat box, please.
Okay,
Well,
so
I think
if you
so. No one
don't have
has.
any, yes,
Ma'am.
okay.
So with this, we come to the end of the session for today. And I would like to thank Dr. Ghosh Madam for such an enlightening talk. She covered all the basics of NMR and MRI, then mathematical analysis, then measurements, analysis, pulse Fourier NMR, and so many other things related to NMR. So thank you so much, ma'am, for sparing your
Okay.
valuable time with us and sharing your knowledge with us. Hope the participants will gain from this knowledge in their future endeavors, and we shall be in touch with you in our future endeavors also. Thank you so much.
Okay, thank you. Thank you
Thank
very
you,
much.
ma'am.
And there is an announcement for all the participants tomorrow after the morning
May I leave
session.
now?
Yes, ma'am. Yes.
Okay. Thank you, ma'am.
Thank you, ma'am. Have a good
Okay,
day.
okay.
There is an announcement for participants tomorrow after the morning session. Immediately, we are going to have the valedictory session for this workshop. We'll not have the valedictory session in the afternoon. We'll directly have after the first session. And we'll share a feedback form with you. It is compulsory to fill that form so that you are going to get the certificate. So please do join in the morning and with us. Thank you, everyone. Have a good day.